this is like quantum mechanics in real life on a scale that's galactic. That's great. That gets me excited.
George, it's good to see you. I wish we can say we planned it this way, but today is the winter solstice and the unique conjunction of Jupiter and Saturn. I think it's the first time in 400 years, and even then they couldn't see it because of the weather, so it may have been 800 years before since people have actually seen it. And it gave me pause for thinking the contrast between what the ancients saw in the sky as major things of importance or uncertainties, and the remarkable transformation we've had to what you've called and what now everyone calls precision cosmology. So as we begin to talk, how do you reflect on this grand human adventure to understand the universe?
Well, I think about it, and I usually end up with three different sort of personal view, depending on what frame I'm talking about. Like, this is the stuff that has come from this, right? Thousands of people are now working on an area which wasn't even worked on when I got started on it. And there's other things like, well, people are doing things that we used to put as memos and they're writing papers about it and all this kind of stuff. I have different feelings at different times about what's going on. But let me go back to your opening, which is the planets aligning. Usually we meet because the stars align. This time we meet because the planets align. And it's actually quite spectacular because it's not just any planets. This is Jupiter and Saturn, and they're really two of the brightest planets in the sky. And they're coming so close together tonight that it's really spectacular to see. So the thing that you could say is any human being was going to be awed by that kind of a thing. And that is something that we share with our ancestors and with everyone else. But now we can see many more things in the sky and know much more about the universe than our forebears could. We've evolved in the last, decades to where we have an understanding of how the universe came into being and how it's developing and where it's going. And that's really a spectacular thing. And so when I started out in doing cosmology, I did it because I knew it was going to be frontier science, and the new instrumentation and new ways were going to make it possible to make advances. But most of the things we knew about cosmology, you could talk about in 45 minutes to a lecture of students, and you could tell them everything that you knew, and it was all on 3 pieces of paper, and that's all. And most things weren't known very accurately. And when I say not very accurately, they were astronomy accurate, factor of 10, that kind of stuff. A few things maybe were known to a factor of 2. One of the things that is still sort of controversial in a much different way was the Hubble expansion rate, called the Hubble constant. How fast is the universe expanding when it is?
Which tells you how fast it's
Still,
expanding and the age of the
right,
universe.
right. And there were still some people that didn't want the universe to expand, but by then most everybody had accepted that. And it turns out that there's only a few key numbers that let you describe the universe. And what happened when we made the discoveries with the Cosmic Background Explorer satellite, COBE, we ran in the position where we were able to take our maps of the sky and then turn around and reduce them eventually to these small number of things, basically 6 numbers. But we were able to measure them with a precision that went from factor 2 to factor of 10 down to where we were talking about 10%. And so I was enthusiastic to say, now we're doing precision cosmology, because I always told my students, you're doing science when you're doing numbers and you're getting them accurately. That's how you know you're doing science, right?
But let me get the
Everything else is just hand waving, right?
let me get the historical framework for this. I think you started in what was then precision cosmology at a much lower level, using balloons and aircraft. As a first effort to that, I actually remember those days. I'm that old. But then COBE was a huge development. So that, I think, it was launched 1989, 1993. So just give a sense of that process, because that was the transformation. It got better and better with WMAP and then Planck, but COBE was the
right.
foundation?
Well, the transformation was when we discovered with COBE that you can see these small variations through the relic radiation from the Big Bang. We can see the small variations that eventually we're going to grow to become the galaxies and clusters of galaxies and larger scale structures, but also give us a hint about what happened in the early universe. And once you had that, then the theorists got all excited saying, if you make these measurements this accurately, you can determine this about what went on and that. So very quickly, we came to understand that by making more and improved measurements, we'll be able to measure the parameters of the universe very well. And I can remember by the time we got to the end of COBE and WMAP was getting ready to be launched, I said, with WMAP, we're going to be getting to the point where we're measuring the universe as well as you do, as a tailor does when he measured your suit.
Wow.
That is,
Okay.
they measure you and they make a suit for you and they put it on, right? Well, we had a model of the universe and it fit as well as a good handmade suit by
Okay.
that time. Now, Planck has come along and moved us, from being at the many times level to the 10% level with COBE to closer to the 1% level with WMAP. So with Planck, many of the things are at the 10th of a percent level, right? But now we're limited by, do we have the right model, the right theory of what's going on in the universe? Or is there something we left out or something like that? But it's quite impressive how much advance has come. And each of those satellites were about 10 years apart. They had 10 years better technology, 10 years better understanding of how to do these measurements, and a lot more excited, bright young people to work on it. So that's a recipe for success.
Now, originally, the beginning concept was the microwave background, which was discovered in the 60s, Nobel Prize from Bell Labs, where they thought it was noise at first, and then they realized it was something more than noise. It was the background of the universe. But originally, they thought it was flat. It was homogeneous, and that the innovation that you came was showed that there were these very small differences. What is it, 1 in 100,000 variations, and those were the key. Once you had that, then you can really develop something. Because if it was all homogeneous, there's just
Right.
one idea. But once you have the variation, then you can really get into it.
What's exciting about it is the universe is very uniform. That says you can make a very simple model of it, but then it had these very small perturbations. So that means you can make a very simple linear model with just small perturbations. So the math is easy as well as doing the understanding of it. The hard part is making measurements at that high precision.
Mm-hmm. Yeah. So, so what I'd like to understand is from the data, and it's calculated, 3 decimal points. You get the age of the universe, the distribution between ordinary matter, dark matter, and dark energy. A little less than 5% is what we call ordinary matter, that we think is everything, but it's less than 5% of the total energy density of the universe. And I've seen all those numbers, but how can you go from the data of the satellites, the 3 satellites, COBE, WMAP, and Planck? What does it give you that enables you to make those calculations of the age of the universe and the energy density?
Okay, this gets a little more complicated. So the first is the universe is pretty uniform. The universe is, if you think about a sphere compared to the Earth is rotating, so it's a little bit of a late, and it also has some mountains and other stuff on it. It's uniform to sort of on the scale of a few in 4,000, right? So it's on a scale of a part in 1,000. The universe is 100 times more smooth than that.
Mm.
But there are these very small variations. That's why it turns out to be easier to do calculations about how the universe formed than how the Earth formed. First, because it's much more linear. Second of all, there's less complicated stuff that goes on in a certain way. So what you're able to do is look at these variations, determine what they must have looked like at the beginning by measuring them carefully with a cosmic microwave background. But even when you're looking a relatively short time, after 300,000 years, 380,000 years after the beginning, it's still 14 billion years to now. So it's if like a human, it's like 6 hours into their, the embryo's lifetime is where you're looking at it. It's very, very, very early. You're able to see some of the variations that happened early, and you can start seeing how it behaves. And an example I give is if you ring a bell, you can hear this tone and you hear this, after it's been ringing for a tiny amount of time, you hear a fairly pure tone if it's a good bell. And if you can see the size of the bell or you have no something else about it, you can tell what it's made out of by the sound, by the frequency of the bell. If you have a steel bell or a silver bell or a brass bell, all physically the same size, they will ring different. So you can tell what the universe is made out of by how these tiny variations are oscillating in the early universe. You can tell what the fluctuations are as a function of scale by looking at different scales. You can look at all the data you have by making a careful map of the very early universe, and you can determine what's the geometry of the universe and what is the universe made out of, as long as you understand what kind of things there can be. So that's why we know about dark matter and ordinary matter and light and things like that, neutrinos. We put all those in and we fit to them and we can determine those things very, very precisely. But it's understanding the same way that people who are skilled musicians or whatever can look at bells and so forth and determine what they're made of or how they're going to sound when they hit them. It's the same kind of experience.
How many different metrics or parameters of the small variations do you measure in terms of the spectrum or the intensity of how many different ways of looking at the variations do you need to make those calculations?
Well, it's how greedy you are into how small you want your errors to be. So what we try to do with Planck, and a lot of that happened not so far from where I am right now, but what we tried to do with Planck is map the entire sky with very good resolution. So with 10 million pixels. So if you print it or or show it on a normal screen, you don't have as much resolution as the map we made of the sky with Planck. Mm. And so there we're talking about 10 million pixels, and we measured it at 9 different frequencies, 9 different wavelengths. So you can separate out what signals might be coming from the galaxy or extragalactic sources and what is coming from the beginning of the universe. And so what you do is a complicated analysis where you reconstruct the images you see of the sky, then you sort them across the different wavelengths or the different frequencies you're talking about, and separate out the components until you have what you think is a map of the primordial universe. You also have a map of the galaxy and a map of other extra sources. And when you do that, you're able then to try and understand it. I'm sorry, my security system is sending me messages. When you do that, you're able then to try and say, okay, what are the various constituencies? Well, you will see that what you see is on large scales, there are fluctuations that are roughly the same amplitude everywhere. And then for some reason it peaks up, and then there's peaks at the harmonics. Those are just the natural frequencies of the universe, just the way ringing a bell has natural frequencies, or a wine glass or whatever. There's some that have very pure tones. The universe doesn't have very many losses, so it has a lot of very pure tones. By measuring those tones, you're measuring the geometry of the universe, in this case, the time from the beginning of the universe to the time you make the image, but also what it's made out of, what's the material of the universe. And so you fit to all these in different, through different ways. And you look to see, is it consistent in this part of the universe and that part of the universe? Do you get the same answer? You can then add it all together, right, and get better statistics and get a more and more precise measurement. And so it's a consistency check. It's a thinking it through carefully. And did I include everything that needs to be included? And so when we're doing this, we're usually doing it with 6 or 7 major parameters, like how much is the dark energy, how much is the dark matter, how much is ordinary matter, how much is these various aspects, plus is there a slight tilt of the spectrum, right? First approximation, you say there's no variation with the amplitude of fluctuations that originally put in there. But then you say, all right, if we think of a more sophisticated model, there'll be a slight tilt to it. We take that into account. And then what's the amplitude and so forth. So you put these extra parameters in. So there's typically 7 or 8, and there's some nuisance parameters in case you've got a background or something else you put in the average over, but you're basically just fitting to a small number. And so you start with 10 million pixels, and then you do a test. Is the universe isotropic? Because you'd have 10 million numbers to describe on it. If it's isotropic, you can collapse that from 2 dimensions to 1 dimension, which means you can do the square root of 10 million, which is very handy. It gets you down to, 3,500 3,000 things. And that's what your basic measurement is those numbers, but then you're fitting 6 numbers to a smooth curve that runs through those numbers. And so it's a complicated process, but simple in a certain conceptual way, but difficult in actually carrying it out and make sure you got it right, and you remove the systematics carefully and everything.
This may sound like a very naive question, but I'm going to ask you anyway. What of the 6, 7 parameters that you use enable you to make this what seems to be a massive distinguishing between ordinary matter, dark matter, and dark energy? These are vastly different kinds of things. And so how can you differentiate between those?
Okay, so there's a phenomenon that we physicists call baryon acoustic oscillations, which is shorthand for saying ordinary matter and light are coupled very well by electromagnetic force. Light tries to shine through the sun, it hits the plasma and it does that. So the early universe is a plasma. Light tries to get through it, hits the electrons, but the electrons are electrically coupled to the protons or the helium nuclei. So there's an oscillation between those 3 fluids, basically. And they make a baryon acoustic oscillation. The light is very powerful in the early universe. It's much stronger, and there's more energy in it than there is in the matter. And it actually tries to blow stuff apart. And you end up, now we see residual spheres of galaxies around a big perturbation. If there was a big perturbation, which was a big cluster of galaxies and dark matter, and they're starting to form together, the baryons get pushed way out. They get pushed out to millions of parsecs, that is millions of, with 3.26 times that is light years. It's many millions of light years, these things get pumped out, and then the light is free to go, and they can form. And a lot of the baryons fall back in on the dark matter, but some of the others don't. And so when you look at that, you can look very carefully. The dark matter has a slightly different behavior in these bumps and lumps that are formed than the ordinary matter. So the ordinary matter goes up and down, the first harmonic, second harmonic, third, it goes up and down the opposite direction than the dark matter. The dark matter just goes up. More dark matter, all the peaks go up. The first harmonic, second harmonic, third harmonic. But the baryons, the ordinary matter, they go up on the first peak, but down on the second peak and so on. So when you increase or change them, they distinguish them. And so because of that, you can do that. But it's not an intuitively obvious thing. You have to sit down. Whoops, sorry, I threw my iPad on the floor by accident. So when you go through and look at this, you have to reason through it carefully and see how they behave. And then it's easy to make up a diagram that shows you that adding matter makes these lumps that appear, that trying to form, bigger. But the ordinary matter gets blown out by the light, and that causes then the harmonics from the dark matter, they all get bigger when there's more dark matter. The harmonics from the ordinary matter, the first one goes up, but the second one goes down, the third one goes up. So even odd kind of difference. Because of those, you can distinguish them and really tell them apart.
Okay,
now, there are other reasons.
That's great between ordinary matter and dark matter, but how about dark energy? Is that just a subtraction of what's left over, or is there some characteristic?
So you have to say when. You have to ask this question when, because before we were saying, the universe looks flat, but the matter doesn't add up to make it flat. So there must be some more energy somewhere to make the universe flat, because Einstein's general relativity tells us the sum of the matter has to be the sum of all the matter, or all the energy, the matter plus energy. So mc squared plus E, all that has to add up to the critical energy density. And there was some missing, right? And so we would say there must be something we're not seeing, and we see it because we're measuring it to be flat, but we're not measuring enough matter, right? And it was then the fact that the supernova, started showing that the universe was, accelerating and getting to be expanding faster and faster now, and all that fit together. There was a little bit of objection at the beginning, but everybody in the field saw it fit together with all the data we were having. It made the universe the right age. It made the universe flat. It made everybody kind of happy, and so they were happy to adapt the dark energy. But we still have to find out what it is. But it got accepted much more quickly than some things get accepted, and so we didn't see at the beginning that it had to be dark energy. We just saw that there was missing energy. Now, with the good results from Planck and now some of the large ground-based experiments, we're getting enough precision that we can actually see evidence for the dark energy from looking at the cosmic microwave background itself. The Rayleigh radiation gives us some information on that. But now you have many more. You have the large-scale structure. You have, the clusters of galaxies are telling us, the supernova are telling us, a number of things are telling us that there's a dark energy.
Yeah, amazing, amazing story. Let's go to some of the work that you've been focused on in recent years, George. And let's start with gravitational lensing, which is a product of Einstein's, obviously, theory of relativity and the bending of light. But give some background on gravitational lensing over the last century, and then describe the kinds of research that you can do today, where this is also part of a precision cosmology, instead of just looking at some blurred images that might be in the sky, but you can actually be very precise on what it means.
Okay, so it's very interesting. I got interested in gravitational lensing more recently, and part of it was I got interested in seeing whether it's phenomena that affect gravity waves, the gravitational radiation that LIGO and Virgo were seeing. I was wondering if some of those could be gravitationally lensed. Could we find a way to see that? I tried being some interested, but we had done as part of Planck, but also part of the other stuff we're doing, using our understanding of gravitational lensing to see how the cosmic microwave background itself was lensed by all the large scale structure between the beginning of the universe and the present. And there's various other ways, but I got interested in the problem of the dark matter too. How can we distinguish the dark matter? And gravitational lensing has a lot of new features coming into bear as we have new and better telescopes in orbit and better things to do. So I got interested in that. And so I talked to two of my colleagues from Mexico, Jorge and Salvador, who had written a historical paper, a brief history of gravity waves a couple of years before that, and said we should do one on gravitational lensing because it's going to have all these applications, right? That people speculated about this for over 200 years, and just like they had, whether there were black holes back to sort of Newtonian era, but it wasn't until general relativity came along that people took it seriously, and the eclipse of 1919, we were coming up on the 100th anniversary when we decided to write this paper. And
that's what demonstrated Einstein's theory to be correct.
Right.
Describe that briefly, because that will give a sense of, in a simple way, of what gravitational lensing.
So I have to make it this year. So I was excited about the new applications, but particularly Salvador and Jorge. But Salvador was really interested in the history, and so he was writing the part on the history. I was writing the part on the formulas and so forth, which actually got cut out of the paper. That's what I meant. They said, it's already in a bunch of other papers. And I said, yeah, I went through all those other papers. And they said, and besides now, anything that looks the same as any other paper, they're worried about whether you plagiarized it or whatever. And I said, well, they run these programs, and of course the equations are going to look the same because you want to use the same notations. But anyway, so we eventually left it out. But he put all the, he went back and did a lot of history and did a great job. I find it interesting, exciting to read. But it goes back to very early times when people were speculating that light could be a particle or a wave, and that if it's a particle, it would be bent passing by the sun or passing by a large body, and calculated the bending, which in those days were able to calculate it, that it should be just less than an arc second, 0.85 arc seconds.
And that's purely by gravitate, by just the Newtonian
just
gravitation.
assuming it's a particle and it's Newtonian, right? And Einstein wrote his general relativity, and he started speculating because it got pushed by several different people, including, you know, people who we would call refugees or immigrants, people who left difficult situations in Europe or other places and came to the US, and a couple of them came by and saw Einstein when he was working in Princeton and convinced him to, you know, or I think it was there, convinced him to actually write an article about it and so forth. And he did, and he thought, well, it'd be too small to ever see, right? but to actually see lensed events. But Einstein had been worried before about seeing the bending of light, and there he got convinced it could be done. That's when he was still in Europe. And eventually he convinced people to do the eclipse collisions that is very famous. There's a really wonderful piece by a very great writer about how dramatic it was for these guys to stand up under the portrait of Newton at the Royal Society and do Newtonian physics in and replace it with general relativity. And but it's a thing. But the lensing he didn't come around to until a little bit later, and he didn't think it would be so useful. And when you look at the numbers, the lensing of stars by stars isn't very likely. But you know, Zwicky and other people realized galaxies could lens galaxies, because galaxies are much bigger and more massive, and the angles and the scales are now on the scales you can measure with astronomical instruments. But it still took until the late 50s before anybody actually saw a gravitational lens and detected it. And they saw it by accident. They were measuring quasars, and they found two quasars had exactly the same spectra. Mm-hmm. And they thought the telescope operator had pointed the same thing twice. And in fact, he hadn't. He pointed the two different images, and they checked with a colleague, and he had time the next night. So he went and measured again with himself watching, and got a better spectra, and found that they were identical. And then they realized they had found a gravitational lens, a quasar that is gravitationally lensed, which is about the best thing. And then people started taking it really seriously. But the theory was there well ahead of time. It wasn't until people started actually observing it that you started taking it seriously. But it's really been the last decade that people have been making tremendous scientific tool out of gravitational lensing and really starting to understand. And, you know, at the time we were writing the paper, there was a very nice paper out by the Very Large Array and looking at a thing that a CMB experiment, the South Pole Telescope, had seen, which they thought was an Einstein ring, and they made a very beautiful image of this with the interferometer, with the big interferometer setup, and it's almost a complete Einstein ring. So if light is bent by a galaxy, and you're perfectly in line behind that, so there's a straight line from the faraway galaxy to the galaxy that's imaging to us, you don't see the light directly, but you see the light that's bent around, and you get a beautiful circle. That's called the Einstein, you know, the Einstein ring, or the Einstein, you know, effect. Although he was the second guy to predict it, he gets the credit because he had the theory that went with it. Anyway, there's a really beautiful image of an Einstein ring that shows it so precisely and so on. So you did that. But then there are also many new images that have 4 or 5 images where you have a galaxy just off behind the galaxy, and you end up with this set of, usually you see 4 bright images. And those are being used to do timing between, you know, the quasar is there. It has a signal. The signal goes up and down. You can look at each of the images and see the signal go up and down. Look at the time delay that measures the geometry that allows you to determine the Hubble expansion rate. So that's
Wow.
one of the things. It's
Wow.
called the holy cow for H0 lensing and so
So
forth.
obviously, the Hubble expansion rate is one of the critical uncertainties today in precision
Right.
cosmology.
There is a controversy going on. It's being stirred up by observations and by some of the people in it, and but there's a discrepancy between the expansion rate people see at great distances, which is also, if you look out a great distance, you're looking back in time. I mean, if you look out a billion light years, you're looking back a billion years. You look 10 billion light years away, you're looking back 10 billion years. The people who are doing the nearby supernova, with nearby supernova and distance scale and so forth, and measuring things locally with Seeber variables, they're getting a different value for the Hubble expansion rate. They call it the constant, but I tried for years to argue that it should be called the Hubble expansion rate, but I lost. Everybody calls it H naught. It's like a constant, but it isn't a constant. It varies in times. The universe was expanding more rapidly in the past, and it slowed down and slowed down and slowed down. And then with the acceleration, the universe started to go back up. And if you look, the theory and the near and the intermediate observations, they all fall on this nice curve.
Mm.
But then the very nearby stuff is too high, right? And so not by a huge amount, it's like 5%. And but nowadays we're in precision cosmology, 5% is huge. and
Almost fine.
so,
But
and so that's a controversy that people think says there's something we're leaving out, or there's that other, or somebody's making a big mistake. It could be any number of things. And it's exciting for the people who are involved.
is gravitational lensing an independent technique that can shed light on that?
Well, the gravitational lensing should be able to shed light on that. The problem is one of statistics. As the new survey comes, we hope when JWST comes up, there'll be more. When LSST comes online, there'll be many more lenses found, and there'll be sufficient statistics to try and use that alternate way to try and determine what's going on. And we'll see what happens.
A basic question with gravitational lensing is you have the image, you can have two or you can have multiple images, as you've said, but there are two things going on. There's the object in the far background, and then there's the lens in the nearer background, the galaxy that's doing. So how do you differentiate from one piece of data the two variables that are causing it?
Yes. So here's where you end up making models, right? And so in the very beginning, people made very simple models of galaxies. They called it an isothermal sphere. That is a constant temperature sphere. So it's just like a ball of gas. Right?
Oh.
And they make a model like that, and then they calculate the trajectories of the light around that. And now people are getting more sophisticated modeling of what the mass distribution might be. And there are other cases that one of the things that I thought was very interesting, and eventually comes to our topic about dark matter, is you can look at a cluster of galaxies, a very large cluster of galaxies, and do gravitational lensing of the fields behind it. Take all the fields through there, and all of them are stretched or elongated or magnified in various ways. You can then try and map it and reconstruct the mass potential, that where the masses are. And so one of the pictures that I sent shows a beautiful picture where you see the cluster is this big kind of a bowl with all these mountains on it, which are the individual galaxies. And that's the kind of thing that you can do with the lensing. You start being able to reconstruct if you have enough statistics. That is, you have a lot of background galaxies, not just one, but many. You can start to reconstruct what is doing the imaging. And we have another example of that, which is the bullet cluster, which is two clusters that have collided with each other and passed through each other.
Oh.
And galaxies, when you have a cluster of galaxies, they go through each other. The galaxies generally miss each other. Mostly it's empty space. The galaxies just go, right? And the dark matter just goes, but the gas goes wham and makes a thermal shock. It gets compressed and makes a thermal shock, and it makes X-rays. And if you look at that, you can see it, the image, you can see it in X-rays in one set of colors. You can see it in, visible light. the galaxies, and then in lensing in blue in the image that I sent. And it's clear you can separate them out, and it's clear that it is, you know, you see that whatever this dark matter is, it doesn't stay with the bulk of the matter, which is the gas. It stays with the galaxies. Now, does that mean there's something magic that galaxies are, or does it just mean the dark matter doesn't interact when it passes through? It just passes through. It's just gravitationally going to come back and eventually merge, right? Just the way the galaxies will. Or, you know, is there some really weird thing going on? Because there are people who try and come up with models that make gravity change depending upon what the ordinary mass is there in order to do that. That's really difficult to do that when you have this kind of example of the bullet cluster. So the lensing in conjunction with the X-rays and the optical really give you a big handle. And that's true of some other lensing. Sometimes you can look in the visible light and see the galaxy and know something about what's going on, as well as doing the measuring of the thing. But yes, it's now a weakness of that. Now, one of the other things, though, that's very powerful is that, have you ever looked in a swimming pool and you see these crazy lines of light in the bottom of the pool? Those are called caustics. Those are places where on the surface waves, the light has sort of focused and crossed. And when it's a very sharp light, they're mostly focusing together, but then they move around and they move away. Well, you get caustics when you look through a galaxy cluster or a galaxy with a lot of stuff in it. You get these caustics if you're right in the right angle and right straight up. If you then monitor with your great new telescope in space, thing in this caustic, when big stars cross across the caustic, or primordial black holes, or some other sort of thing cross across that caustic, you will see this interesting variation that goes on. Or in the model that we have of the really strange kind of dark matter, where it's wave dark matter and you have this complicated wave structure, it will cause that caustic to have this extra waviness to it, like my tie or something. It's a you know, so it turns out there are many new tools coming up that are starting to be exploited, but we're in a situation where we think, oh yes, we're going to have good time now. We're going to have a lot of new data, a lot of new things to see.
George, let's talk about dark matter. You alluded to it, what as I have followed the field, I am constantly amazed at the vast orders of magnitude difference in terms of what may be the cause of it. It's not controversial at all that there is dark matter. The evidence for it in terms of star speeds around centers of galaxies are undeniable. So that everybody agrees that there is dark matter that is gravitate. But what it is such a broad dispersion in orders of magnitude. I think you are at the very smallest, and I want to understand that, something like 10 to the minus 22nd electron volt, and then if you go to the other extreme, WIMPs, weakly interacting massive particles, that's a billion or a trillion, 10 to the 9th, 10 to the 12th electron volts. So between the two, you have orders of magnitude difference of 10 to the.
You're not going far enough. You're not going far enough. We're thinking it could be down as low as 10 to the minus 22 eV. That's one of my favorites because it's kind of cool. But on the other end, it could be primordial black holes.
Yeah, I can't even calculate what that would mean, because that's 10 to the 30th.
Yeah, well, it's macroscopic. It's stuff that is huge, right? Yeah. A small, a 30 solar mass black hole is bigger than New York, right? Not a lot, but big. And so the thing is, we know some stuff about the dark matter. That is, anybody who is fact-based or whatever it is, I was going to say, sensible people in physics and astrophysics really believe there is dark matter, even though a lot of people don't like it, right? They didn't like having to add these new ingredients. I mean, dark matter and dark energy, and only 5% of what we know is stuff we know. And that's not a good advertisement. But the fact is, almost everybody understands there's dark matter, and almost everybody understands it has to be predominantly what we call cold dark matter, or at least very cool dark matter. That means that at the time when the matter and the radiation separated, that matter was cool enough that it could clump up by itself under its gravitational stuff. And that means it's non-relativistic, right, compared to whatever it is. Now, neutrinos could be non-relativistic, except all the neutrinos we know have a very low mass, so they stay fairly relativistic. So if there's another neutrino we don't know about, whatever it is, so the part of the dark matter is neutrinos, but it's a very tiny part, and it's not so cold. Whatever it is cold. Now, what can be cold? Well, we thought WIMPs could be cold. They're these heavy massive particles that only interact weakly, and by gravity, they can naturally be cold. And primordial black holes can be cold because they'll just act like giant WIMPs, right? But how can something whose constant wavelength is, light years, how can that possibly be cold? Well, the answer is, if it's a boson, that is, if it's a kind of particle that Bose and Einstein carried, as opposed to Fermi and Dirac, it has an integral spin. In this case, we're thinking something can spin zero, which nobody knew of before 10 years ago that any existed. Then it can condense into a single quantum state. So you can imagine you have this thing that's huge in wavelength, tiny, tiny in mass. That's because the Planck's constant divided by the mass basically is giving you an idea of the wavelength. If you do that and you imagine you put a really large number of these together, so you have a Bose-Einstein condensate. So we have colleagues in condensed matter atomic physics that make atom Bose-Einstein condensates or something like that, and they have a large number, like a million. It's a really big thing. But here we're talking astronomical numbers, right? So that you're going to have a mass which could be equal to the central bulge of our galaxy, right?
Wow.
And then you have this thing that acts like a classical quantum mechanics. So I don't know exactly how to say, a non-relativistic quantum mechanic kind of a situation where you have a central soliton, which is a single Bose-Einstein condensate, and then slightly excited states of that same material that are orbiting around it. And that looks just like cold dark matter, as long as you were to get away from the central soliton. So in practice, on the big scale, as soon as you get outside the scale of the center of a galaxy, it looks like that, except for the fact that it's wavy. It's, it's got all these de Broglie wavelength fluctuations all over the place, whereas the WIMPs would just be kind of a smooth soup and that kind of thing. And so they're not so different, but they're really, I mean, this is like quantum mechanics in real life on a scale that's galactic. That's great. That gets me excited. I used to not like black holes very much until I started teaching a course about it. The students loved it. Now I would love it to get to teach them about large device.
Is there any possible experimental evidence that could distinguish between the two, between WIMPs and what you have as the super ultralight Bose-Einstein condensate?
So the answer is yes. There's several things that could distinguish them. I have a simple one with some of my colleagues where if you had in our galaxy and you had pulsars in our galaxy, you could look for, the frequency changing because this is a quantum state, it's oscillating at its Compton wavelength, it's in a Compton frequency, it's oscillating, its potential will change, it will change its frequency, it'll change its phase. You could do that, but you need to have the pulsar in the right place and another pulsar to compare it to so you can see. But we've been trying to look at data on dwarf galaxies. Dwarf galaxies should have a core that's made of this condensate, but as you try and make it smaller, you can't. As you try and make a lower mass galaxy, it actually has to expand because the de Broglie wavelength gets larger. And so by looking at these dwarf galaxies, you can try and look and see that. And we've also looked at this stuff, and we also want to do the gravitational lensing and look along a caustic and see if we can see the waviness of the caustic that comes from the wave nature. And so that's one of the ways you can distinguish it. We want to do a series of experiments that can distinguish between the primordial black holes, the WIMPs, And then, so we know which way to be pursuing it. And it's kind of fun to work with the wave dark matter. It's, it's new and different, right?
Well, George, this looks to the future in terms of the kinds of experiments that will continue to make precision cosmology even more precise and answer not just questions of decimal points, but now distinguishing between two radically different mechanisms of what dark matter is. So as precision cosmology develops, what I'd love you to do is kind of look to the future. We've enjoyed looking to the past, but look to the future, the next decade, the next several decades. What are the kinds of progress that are being planned and that you hope to see?
Okay, so you get progress in science, A, when you free your mind and think about new things. You could do that anytime, but somehow, usually some new thing has to come up. Then B, when you get new ways to observe things, new technology, new detectors. And so we have a whole bunch of those. We expect within the year from now, the James Webb Space Telescope will be launched, and that will allow us to do probing out to a higher redshift and with a bigger angular resolution, so we can do it in the infrared. And that'll let us probe back to the earlier times of the universe. We expect that there will be a next generation of cosmic microwave background experiments that'll try and measure things on the really smallest angular scale much more precisely. That requires bigger dishes that look smaller. And we expect that LIGO and Virgo are joined by COGRA, and then eventually, within the decade, by LIGO India.
The waves. Yeah.
Right, and so gravitational waves will be providing us more information. And then LISA, in space. So there are going to be new devices and new data, new observations coming in. And that should jar us and to be thinking about new stuff. And what we can hope is some brilliant person will come up with some theoretical ideas that will kick us over. Now, the problem is there's 1,000 theoretical papers a year and none of them are right so far, but, or at least so we can tell. The problem is, you don't give them credit. You give them credit if it's a good idea and if it might lead to something later, right? Because there are not too many times you make a big breakthrough. But the fact is, we depend on the theorists to think about new ways that we can look at the data so that we can test things and see what we're trying to find out.
What's your best guess of where we'll be if we have another meeting like this, 20 years from today, and you and I look exactly the same, and we're very, very buoyant, and looking back on the 20 years in the future from now until then, what do you think you'll be able to say?
Right. So right now, I'm not foolish enough to try. Having the COVID-19 pandemic come up and just throw all my travel plans and all my projections completely in disarray within a month. I mean, I kept, and for a while, 2 or 3 months, I was thinking, well, it'll get back to normal. Now I'm thinking, oh, it'll be good if it gets back to normal by next fall, and we'll see what happens. But it gives you a different perspective. However, I have to think we're going to be making progress, and it's going to be still exciting to be in cosmology. So I have a story I can tell. So I don't know if you know who Chandrasekhar is. He was a famous Indian physicist, but he was at the University of Chicago. He would work in the field and make a bunch of advances and move on, because he said every 10 years you should move on so that you sort of cleaned up what you know, and the young people have a chance to go on and you can move some new area and do that. But he did that until he got to cosmology, and he stayed in cosmology for a while and then he died. But and I'm saying, I think cosmology is going to last a while longer because it's really broadly defined subject. And so, normally a field would get kind of filled up, but the universe is a big place and there's a lot of stuff to do and look at. And so it's really hard to predict which way we're going, what's going to go on. But I think, we could be lucky, and we could get to the point where we're saying, oh, we did pretty much everything. Like, we got to go look at a different field. That'd be great. That means I lived through the peak time, but and we know the answers now. But because there's still a lot of stuff I want to know the answer to.
20 years from today, you have a date. We're going to get back and we'll look back on those 20 years and see what happened. It's really been a remarkable ride, and I look forward to the future. Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.